All right, so everyone's talking about AI these days, but how do we really grasp this idea of computational complexity in machine learning?
Yeah, it's like trying to figure out, if a recipe is a quick weeknight dinner
Right.
or a full-blown weekend project, right?
Exactly.
Some algorithms are really simple and efficient,
Hmm.
while others need a ton of computing power and take ages to run.
Yeah, that makes sense.
The word complexity can actually be a bit tricky in machine learning
Okay.
because we hear about computational complexity
Right.
and model complexity,
Okay.
but they're actually totally different things.
Gotcha.
And understanding that difference is really important because it affects how well and how fast these machine learning systems actually work.
Okay, so let's untangle those two then,
Okay.
starting with computational complexity.
So think of it like this: computational complexity is all about how efficiently an algorithm uses its resources,
Okay.
like processing time and memory.
Hmm.
It's kind of like judging a chef, not just by, how tasty their dish is,
Yeah.
but also by how quickly they can whip it up
Okay.
and how much they make a mess in the kitchen.
Uh-huh. So computationally complex algorithm is like a chef who makes an amazing meal but takes forever and leaves a huge mess.
Exactly. You got it.
Okay, I like that analogy.
And then on the other side, you have model complexity, which is all about the inherent, sophistication of the model itself.
Okay.
Its ability to learn those intricate patterns from the data.
Mm-hmm.
So it's about whether the recipe can produce a simple omelet
Right.
or like a multi-layered masterpiece,
Yep.
right?
Yep.
A more complex model might be able to catch those really subtle nuances in the data,
Yeah.
but it might also need way more computational resources to train.
So it's like needing a bigger kitchen and more fancy tools to make that really elaborate dish.
Exactly. It's a trade-off.
Gotcha. So it's like this trade-off.
Right.
A more complex model might be more powerful,
Mm-hmm.
but it could also be a lot slower and more resource intensive.
Yeah, precisely. When we talk about computational complexity, there are three main things to keep in mind: time space and sample complexity.
Okay, those sound kind of familiar. Let's break those down,
Okay.
starting with time complexity.
Right.
I'm guessing that's basically about how long it takes an algorithm to actually run.
You got it. Time complexity measures how the processing time increases as the amount of input data grows.
Okay.
Think about sorting a deck of cards. A larger deck is naturally going to take longer to sort no matter how fast you are.
That makes sense. And what about space complexity then?
Okay, so space complexity is all about memory usage.
What?
It's like how much counter space you need to work on that fancy dish
Right.
as the input data grows.
Yeah.
Does the algorithm need more and more counter space?
Okay.
Or can it work with a
Sure.
smaller space?
Got it. So time is about speed and space is about memory.
Mm-hmm.
What about this third one, sample complexity?
Okay, so sample complexity is how much data an algorithm actually needs to learn effectively.
Okay.
Some algorithms are quick learners and can do well with just a small sample,
Mm-hmm.
while others need a ton of examples to really master something.
Okay, so it's like some people can pick up a skill from like a 5-minute YouTube video,
Right.
and others need weeks of practice to get it.
Exactly, you got it.
And that makes sense.
Before we dive deeper into these, though,
Right?
maybe let's take a little detour through the history of artificial intelligence,
Okay.
machine learning, and neural networks, just to give a bit of context.
Yeah, I think that would be helpful.
So the whole idea of intelligent machines has been around for centuries,
Mm-hmm.
but the field of AI, as we know it,
Right.
really emerged in like the mid-20th century.
Okay.
Early research in AI was all about symbolic reasoning
Okay.
and these rule-based systems
Mhm.
trying to build intelligence by like handcrafting rules for every situation.
So it was like trying to program a computer to think like a human by writing down every single rule of logic.
Precisely. And it turned out to be really, really hard.
Yeah, that sounds really hard.
And then came machine learning, which is a totally different approach, where algorithms learn from data instead of being programmed explicitly.
Ah, so instead of trying to program every rule by hand, we let the machines figure out the patterns on their own.
Exactly, major shift.
Gotcha.
Early machine learning algorithms were surprisingly effective in areas like image recognition and spam detection.
Okay.
But the real game changer was neural networks,
Okay.
which are modeled after the structure and function of our own brains.
Right. Neural networks and deep learning. Those are the terms that everyone's talking about these days.
They are, and for good reason.
Yeah.
Neural networks are basically these interconnected nodes or neurons
Okay.
that process information, kind of like how our brains work.
Mm-hmm.
And when you have multiple layers of these neurons, you get a deep neural network,
Right.
which can learn really complex patterns
Okay.
for huge amounts of data.
So it's like giving the machine a much more powerful way to understand the world.
Precisely. Deep learning has been revolutionary for so many fields,
Yeah.
but this power comes at a price.
Okay.
Deep learning models can be super computationally demanding to train.
So we're back to that trade-off between power and efficiency.
Right.
How do computer scientists actually measure this efficiency?
Well, that's where big O notation comes in.
Okay.
It's basically a shorthand way of describing how the time and space requirements of an algorithm increase as the input size grows.
So instead of saying this algorithm takes 10 seconds to run, you'd say something like this algorithm has a time complexity of.
Exactly. Big O focuses on the overall trend,
Okay.
the growth rate, not the exact numbers.
Okay.
It lets us compare how different algorithms scale up without getting bogged down in the specifics of the hardware
Right.
or how they're actually implemented.
Gotcha. So big O notation helps us understand how an algorithm's performance changes as the data grows. Can you give me a specific example of how this actually plays out?
Absolutely. Let's look at sorting algorithms.
Okay.
A classic example of how different approaches can have wildly different computational complexities. Let's say you have a deck of cards and you want to sort them. One way is to use a simple algorithm called bubble sort.
Okay.
It goes through the list over and over,
Oh,
compares elements that are right next to each other,
right.
and swaps them if they're in the wrong order.
Sounds pretty straightforward. What's wrong with that?
Well, bubble sort works for small data sets,
Okay.
but its time complexity is O of n squared.
Okay.
This means that as the number of things to sort, which we call n,
Right.
increases, the processing time grows quadratically.
Okay.
So if you double the number of cards, the sorting time could increase by 4 times.
So it gets really inefficient with more data.
Exactly.
What would be a better way to sort a large deck of cards then?
Well, an algorithm like merge sort is much better.
Okay.
It uses a divide and conquer approach, dividing the list into smaller sublists,
Okay.
sorting those, and then merging them back together in order.
Okay.
Its time complexity is O of n log
Okay.
n, which means it scales way more efficiently than bubble sort for larger data sets.
Okay, so merge sort is like a more organized and strategic way to sort. Well, bubble sort is kind of just brute force.
You got it.
Gotcha. So this shows how understanding big O notation can help us choose the best algorithm for a certain task,
Exactly.
especially when dealing with lots of data.
Exactly. Especially when n is big.
Right.
Yeah.
This is making a lot more sense now.
Good.
So we talked about time and space complexity using big O notation.
Right.
Now let's go back to sample complexity.
Okay.
Could you tell me a little more about that?
Of course, sample complexity, as we touched on earlier,
Yeah.
is about how much data an algorithm needs to learn well. And this is related to a cool concept from information theory
Right.
called entropy.
Entropy. Now that sounds interesting.
It is. Entropy basically measures the uncertainty or randomness in data.
Okay.
And in machine learning, it helps us understand how much info is needed to make good predictions. Imagine you're trying to guess what someone's thinking. The more random their thoughts are,
Yeah.
the higher the entropy and the harder it is to guess.
Right.
But
So high entropy means more uncertainty,
exactly.
which means an algorithm might need more data to learn well.
Exactly. And this goes back to sample complexity.
Right.
If the data has high entropy,
Yeah.
like lots of randomness, we'll need a bigger sample size to train a model that can actually predict things accurately.
Okay, so entropy is like a measure of how much surprise is hidden in the data.
That's a great way to put it.
The more surprises,
Yeah.
the more data we need to figure it all out.
Exactly. And understanding these ideas can be so valuable in machine learning because they help us grasp the basics of learning and prediction.
This is all fascinating.
Yeah.
We've covered so much.
We have.
From defining computational and model complexity to that little trip through AI history.
Yeah.
And we explored big O notation, sorting algorithms, and even entropy.
Yeah.
And all these ideas are connected. And they're important for understanding the trade-offs between how powerful a machine learning model can be
Right.
and the computational resources it takes to make it work.
Absolutely. It's all connected.
Okay, so now that we have this good foundation, are you ready to jump into the world of generative models?
Yeah.
And see how these ideas apply there?
Absolutely. Generative models are super exciting and they're changing so fast.
Okay.
And understanding what they need computationally is really important as we push the boundaries of what's possible.
All right, let's do it.
Okay. Generative models are kind of a different breed, you know?
Look.
Unlike their discriminative cousins that are all about classifying or predicting things, generative models are all about creating, bringing something new into the world.
So we're talking about AI that can write poems or compose music or even create those like photorealistic images,
Right.
that sounds almost magical.
Yeah, it does have a magical quality to it.
Yeah.
And yes, those are all examples of what generative AI can do. But the real magic is in the math and the algorithms,
Right.
not in some mystical force.
Gotcha.
Generative models learn the patterns and structures within a data set,
Okay.
and then they use that knowledge to generate new data points that share those same characteristics.
So it's like the AI is studying a giant book of sheet music
Mm-hmm.
or a collection of famous paintings,
Right.
and then using what it learns to compose a new song or paint a brand new masterpiece.
Precisely. And the complexity comes from the fact that these rules of creation can be incredibly subtle and intricate,
Right.
especially when we're dealing with things like language or imagery.
Yeah.
A generative model that can write a convincing poem needs to understand not just grammar and vocabulary, but also things like rhythm, rhyme, and metaphor.
It's not just stringing words together.
Right.
It's about capturing that essence of human creativity.
Exactly.
And it's kind of fascinating to think about how the idea of generative AI goes way back,
Yeah.
even to ancient myths and stories about creation, this connection between those age-old desires
Yeah.
and this cutting-edge technology.
It is fascinating. And while the term generative AI is pretty new,
Okay.
the ideas behind it have been around for decades.
Right.
Early experiments with language processing and pattern recognition really paved the way for the models we have today.
Makes sense.
And as we push the boundaries of generative AI,
Yeah.
creating models that can generate even more realistic and complex outputs,
Right.
the computational demands just keep growing.
So it's like we're constantly raising the bar
You're right.
for what these models can create.
Exactly.
And that requires more and more power.
Exactly. Researchers are always working on new algorithms and techniques to try to improve the efficiency of these models.
Okay.
But it's a constant challenge,
Yeah.
especially when you consider just how much data is involved
Right.
and the complexity of the models themselves.
Yeah, that makes sense.
Yeah.
Now, I know we wanted to talk about a specific type of generative model that's been getting a lot of attention lately. Large language models, or LLMs.
Yeah, LLMs are fascinating.
Okay.
They're a subset of generative models that specialize in understanding and generating human language.
Okay.
They're trained on massive amounts of text data,
Right.
which allows them to do a wide range of language tasks,
Okay.
from translating languages to writing different kinds of creative content.
So it's like giving the AI access to this giant library of books and articles and every tweet ever written.
Exactly. That's what makes LLMs so powerful.
Yeah.
They have access to so much human knowledge,
Right.
and they can use that to generate text that sounds surprisingly human-like.
Okay.
But this power comes at a cost. LLMs are known for being very computationally demanding to train.
Right. Brings us back to computational complexity.
Exactly. Remember our earlier discussion about big O notation?
Yeah.
Well, with LLMs, we often see complexities that grow exponentially. With the size of the model and the amount of training data.
So if you want to create an LLM that can write a whole novel or have a deep philosophical conversation,
Right.
you're going to need a lot of computing power.
You need a ton.
Yeah.
Training an LLM can take weeks or even months
Wow.
of computation time on specialized hardware.
Cool.
And the energy consumption can be significant.
Yeah, that makes sense.
So why are LLMs so computationally demanding? Well, there are a few things that contribute to that.
Oh.
One is the sheer size of these models.
Right.
LLMs can have billions or even trillions of parameters,
Okay.
which are basically the variables that the model adjusts during training to learn those patterns in the data.
So it's like having this giant machine with billions of tiny knobs
Yeah,
that need to be perfectly adjusted
exactly.
to produce coherent language.
That's a great analogy. The more knobs you have,
Yes.
the more complex that tuning process becomes,
Right.
and the more data you need to find the right settings.
Okay.
Another thing that adds to the complexity of LLMs is the use of a technique called self-attention.
Self-attention. That sounds interesting.
It is.
Yeah.
Self-attention allows the model to focus on specific parts of the input data,
Okay.
kind of like how we humans selectively focus our attention on the most important parts of a conversation or a piece of writing.
Okay.
It helps the model understand the context and nuances of human language.
So it's like the AI is learning to pay attention to the right cues.
Exactly.
Just like we do in a conversation
Sure.
to
Yeah.
figure out what's really being said.
Exactly. And this ability is super important for LLMs
Okay.
because it allows them to generate text that is not just grammatically correct,
Right.
but also meaningful and relevant.
Okay.
But here's the thing. Self-attention is computationally expensive.
Ah, well.
It involves comparing every word in a sentence or a paragraph to every other word,
Okay.
leading to a quadratic increase in computational complexity
Gotcha.
as the text gets longer.
So it's like the AI is having this massive internal dialogue, trying to figure out how all the pieces of language fit together.
Exactly. And that's why it needs so much power.
Okay, that makes sense.
And that's also why researchers are always looking for ways to improve the efficiency of self-attention mechanisms,
Okay.
and reduce the computational burden of these LLMs.
Yeah.
There are different techniques being developed all the time.
Okay.
It's a really active area of research.
So we have these really powerful but computationally demanding LLMs
Right.
that are really pushing the boundaries of what's possible with language. But where does it all lead?
That's the big question.
What are the implications of this increasing complexity as we develop even more sophisticated models?
Well, one implication is that we're going to need more powerful and energy-efficient hardware.
Okay.
As we create bigger and more complex models,
Right.
we'll need specialized chips and infrastructure to handle the load.
Yeah, that makes sense.
We also need to think about the environmental impact.
Okay.
Training these massive models uses a lot of energy. So we need to explore ways to make AI more sustainable.
So it sounds like we're at this point where the progress of AI depends not just on making smarter algorithms, but also on building the infrastructure to support them.
Exactly, and doing it responsibly.
Right. And speaking of responsibility, all this talk about AI getting more complex makes me think of those sci-fi movies
Yeah.
where machines become so smart they like take over
Right.
and start making their own decisions,
Yeah.
often with some pretty bad consequences.
Yeah.
Is that something we should actually be worried about?
That's a question that people have been debating for a long time.
Right.
It's important to think about the potential risks,
Yeah.
but it's also important to be realistic.
Okay.
The truth is, AI is a tool.
Right.
Like any tool, it can be used for good or for bad. It's up to us to guide its development and use it ethically.
So it's not about being afraid of the technology.
Yes,
It's
no.
about understanding it and using it wisely.
Exactly.
Okay, so going back to the technical side of things, I think it's interesting how this idea of computational complexity goes beyond just the algorithms themselves. Remember when we talked about sorting algorithms?
Yeah.
Like choosing a better sorting algorithm can save a lot of time and resources.
Exactly. And what's interesting is that how efficient those sorting algorithms are
Yeah.
can actually affect other algorithms and processes.
Oh, okay, how so?
A lot of machine learning algorithms rely on finding patterns in data.
Right.
If the data is already sorted,
Yeah.
those patterns are much easier to find. It's
Yeah.
like trying to find a book in a messy library versus a well-organized bookstore.
Right, so it's like prepping the data to make it easier for the AI to learn from.
Precisely. And this shows that computational complexity isn't just about making each algorithm faster. It's
Okay.
about the whole system. Sometimes even a simple step like sorting the data first
Right.
can really speed things up.
It's like having a good foundation before you build a house.
Yeah, a great analogy.
A strong foundation makes everything smoother.
Exactly. And this interconnectedness is important as we learn more about AI. Even small improvements in efficiency can add up to big gains.
This has been a really insightful deep dive.
It has,
We've covered so much,
Yeah.
from the basics of computational and model complexity to the history of AI and the challenges of generative models and LLMs.
we did.
It's clear that computational complexity is a key part of AI,
It is.
and it's only going to become more important as these technologies keep evolving.
Absolutely. And what's really exciting is how these ideas that come from computer science
Yeah.
have implications that go way beyond just the technical stuff.
Okay.
They raise questions about human ingenuity, the nature of knowledge,
Wow.
and how to use these powerful tools responsibly.
It's like computational complexity is a lens to view not just what AI can do,
Yeah.
but also the challenges and opportunities we face as a society
Well said.
as we figure out how to live with these technologies.
Exactly. As we wrap up this deep dive, I want to leave our listeners with one last thought.
Okay.
We've talked a lot about how computational complexity can limit what AI can do.
Right.
But what if we look at it differently?
Okay.
What if instead of seeing complexity as a barrier,
Yeah,
we see it as a new frontier to explore?
I like that. turning a challenge into an opportunity.
Exactly. Imagine a future where AI has a ton of computational power. It
Wow.
can solve problems that we can't even grasp right now.
Right.
Problems like understanding consciousness,
Okay.
simulating the beginning of the universe,
Wow.
or even finding solutions to global problems.
Like climate change.
Exactly.
Right.
Climate change and poverty.
It's a pretty bold vision,
It is.
using AI to push the limits of human knowledge.
Exactly. And while it would take a huge amount of computational power,
Yeah,
the potential benefits could change everything.
that's amazing.
It's a challenge that needs not just faster computers,
Right.
but also new algorithms and a deeper understanding of complexity itself.
So it's not just about building bigger machines.
Right.
It's about expanding what's computationally possible.
Exactly. And that should get anyone excited who's interested in the future of AI.
For sure.
So, as we end this deep dive,
Okay.
we leave you with this invitation.
Okay.
Embrace complexity.
Mm-hmm.
Explore it.
Yeah.
And let your curiosity lead you on this incredible journey of discovery.